The objective of this video is to analyze the operation of the buck switch mode converter. We're going to be drawing from the content of several of the previous videos in order to formalize the analysis of this converter. So, as is typical for these videos, let's start by considering the buck converter in its single pole double throw switch configuration already sketched in your video. Right off the bat, let's start with an exercise, and I'd like you to sketch the semiconductor switch realization of this circuit by replacing the single pole double throw switch with the semiconductors, the MOSFET and diode that are required. Note that we've defined this so that we have a larger voltage on the left side of our converter, and that is our source voltage. We're reducing it down to a lower output voltage. That is the fundamental idea behind a buck converter, is that it bucks the voltage down from the source voltage to the load voltage. So you can press pause now and press play when you're ready to resume. So I've sketched our converter on the right, and you'll see that this is using the semiconductor realization for a positive pole current. By definition of how we've set this up, the pole current has to be positive. We're providing a power from our source and into our load, which means that IP must be positive. And you'll see that in this circuit, I've labeled the gate signal for the MOSFET as Q, and I've added a capacitor and a load resistor. So the capacitor is going to be considered a little bit more towards the end, but this is the practical implementation, is that we have a capacitor here that we can model as an equivalent voltage source. And then we're modeling our load this time as an equivalent resistor, which has a value of R sub L. So when you operate this converter, it takes one of two states depending on whether the MOSFET or diode are conducting. We'll sketch those states now. The first state is when the MOSFET is conducting, and at this point our entire input voltage is directly applied to our inductor plus our output voltage. So I've sketched the output voltage again as a voltage source. And so if our MOSFET were drawn, it would be at this location, and we would have an open circuited diode down here. Our second state corresponds to the diode conducting and the MOSFET turned off. In this case, we do not see the input voltage. Instead, the input terminal of our inductor is short-circuited to the common. So our diode is at this location, and it appears as a short circuit, and our MOSFET would be up here. And we'll go ahead and label some of our currents here. So I'm now going to construct a table for what the various circuit quantities look like in each state. The first quantity of interest is going to be the total time that we reside in each of the states, whether we're in state 1 or state 2. And the amount of time that we spend in state 1 is going to be expressed as D times TS, where D is the duty ratio of our MOSFET, and TS is the switching interval for the converter. 1 over TS is our switching frequency, Fs. So if our MOSFET is on D% of the time, that means that we are in state 1 D times TS seconds. Similarly, whenever we are not in state 1, we are in state 2, which means that we are in state 2 for 1 minus D times TS seconds per switching interval. So this means that we are either in state 1 or in state 2 at all times for our circuit. When we're in state 1, we can write an expression for what the drain to source voltage is of our MOSFET, and if the MOSFET's conducting, we assume that this is 0. Or if you want to get very specific, you can say that it's the throw 1 current times the drain source resistance of the MOSFET. But for this analysis, let's assume it's 0. When we're in state 2, our MOSFET is off, and it has to block the entire input voltage. So its drain to source voltage at that point is Vin. And you can see that from the above circuit of state 2. If you were to draw the rest of the circuit, you'd have your input voltage here, it'd be connected to your MOSFET, and your MOSFET would be connected to the return of the input voltage. So clearly it has to block the entire input voltage. Our diode voltage, when you're in state 1, the MOSFET's conducting and the diode is off. And as we can see in our circuit above, this means that the entire input voltage appears across our diode, so it has to block Vin. And in state 2, the diode is conducting, so it has to block no voltage. The current across our inductor in state 1 is clearly equal to Vin minus Vout. But in state 2, it is clearly equal to a negative Vout. The inductor current during state 1 is increasing because we have a positive voltage across the inductor, but in state 2 it is decreasing. And our input current, In, during state 1, the pole is connected to the top throw, so it's simply equal to IT1, which is going to be equal to our inductor current. And during state 2, it must be 0. There is nothing connected to the top throw. We can now summarize the steady state analysis expressions for the buck converter. As we previously talked about, the voltage across the pole of the single pole double throw switch is going to be equal to the duty ratio of the pole connected to the top throw times the input voltage. So Vp is equal to D times Vin, where D is the duty ratio of the MOSFET, or in other words, it's the duty ratio of the pole being connected to the top throw. And the average value of this is simply equal to our output voltage. This is an important expression for the buck converter. If we know what we want for our output voltage and our input voltage is specified, we can calculate our duty ratio as Vout divided by Vin. We can determine the average of our input current as being equal to the average of the throw 1 current, which is clearly equal to our duty ratio times the average of our output current, or the average of our inductor current. So the pole is connected to throw 1, on average D percent of time, the duty ratio percent, and so therefore the current going through throw 1 must be equal to D times the pole current, which is also equal to the average of our output current. And this is an important expression because it tells us the average current that our MOSFET has to carry. And in this example, I'm talking about MOSFETs, but this could be BJTs, it could be IGBTs, it could be different versions of MOSFETs, for example, silicon carbide or gallium nitride. But we've decided to draw this as a MOSFET. So next we can do Kirchhoff's current law around our throw 2 current, our average throw 2 current, and we can establish this as a supernode equation where clearly the sum of our throw 1 current plus the sum of our throw 2 current must be equal to the average of our pole current, or our output current. And we can rewrite this as saying that IT2 is equal to Iout minus IT1, and these are all average expressions again. And we've already established that Iout is equal to D times, I apologize, we have already established that IT1 is equal to D times Iout. So we find that the average of our throw 2 current is 1 minus D times Iout. And this is important because this quantity, the average of our throw 2 current, represents the average current that our diode has to carry. Finally, we can summarize the steady state power flow equation as saying that our output power must equal our efficiency times our input power. And if we express this in terms of the average current quantities, we can write that our output voltage times our output current must be equal to our efficiency times our input voltage times our input current. So with these expressions, you get the complete steady-state analysis of the buck converter. Let's now sketch some waveforms. And the first waveform that we're going to sketch is our sawtooth carrier for implementing the pulse width modulation. We're going to assume that our carrier goes from 0 to 1 and then restarts at 0. So that means that at time ts, our carrier will be peaking at 1, and at time 0, our carrier will have a value of 0. And if we sketch our duty ratio on here as a horizontal dashed line, we can identify when our turn on and turn off intervals will occur. You'll notice that I've labeled our MOSFET gate signal as being Q, where Q is either a logic low or a logic high, so we'll say it's either a 1 or a 0. And it's a logic high when our MOSFET should be on, and a logic low, a 0, when our MOSFET should be off. As we previously talked about, whenever our comparator waveform, whenever our triangle carrier waveform is greater than our duty ratio, we will have the MOSFET on. And whenever our carrier waveform is greater than the duty ratio, our MOSFET will be off. So when our MOSFET's on, we are in state 1, as we've labeled in our diagram. And when our MOSFET's off, we are in state 2. We previously noticed that when we are in state 1, our inductor voltage is equal to Vin minus Vout. And when we are in state 2, our inductor voltage is a negative Vout. And we can use this waveform to calculate the ripple in our inductor current, as we've previously discussed. So I'll call this first area area A, and the second area area B. And according to our previous discussion, area A must equal area B in order for the inductor to have an average steady-state value. If one of these areas was bigger than the other, the inductor current would trend upwards or downwards. And we can calculate the ripple current in our inductor by using these areas, which comes from the differential equation of an inductor, and results in the following expression. So we can now draw our inductor current waveform, which is going to be a little bit crowded on this diagram. But we know that our inductor current has an average value which is equal to the output current. And we're going to compare this later to other types of DC-DC converters where the inductor average current is not always equal to where the average inductor current is not always equal to the average output current. So this is an important thing to take note of. In the buck converter, the average inductor current is equal to our average output current, and it has a ripple value as we've previously calculated, and we can note that the inductor current is going to be increasing over the interval where it has a positive voltage applied across it, which is to say over the interval of stage 1, and it's going to be decreasing over the interval where it has a negative voltage applied across it, which is the interval of stage 2. Next, if it's important to us, we can also analyze the current going into the capacitor. So for this analysis so far, we've been considering our output load to be an equivalent voltage source, Vout. But in actuality, it's presumably a capacitor combined with a resistor, where the capacitor acts like a filter to stabilize our output voltage. So this analysis so far has required our output voltage to be perfectly stable. And this is consistent with our approach to analyzing power electronic circuits, that we try to simplify things as much as possible to study only one portion of the circuit at a time. However, now, in order to study the capacitor current, we have to acknowledge that our voltage, our load voltage, actually does change. So instead of modeling our load as an equivalent voltage source, we're going to model it as an equivalent current source where the load current is DC. And the current going into this branch is simply our inductor current, IL. So to summarize here, before we go any further, we've determined our inductor current value by treating our load as a fixed voltage equal to V out. Now we're going to determine our capacitor current by using our previously determined inductor current with a load that's modeled as a DC current source. And so we can sketch our capacitor current as being equal to IL minus our output current, which is to say that our capacitor current is just simply equal to the ripple current waveform of our inductor. And we can then use this expression to calculate the ripple in our output voltage. As we previously discussed, we do this by considering the total charge that's flowing in and out of the capacitor. And over one switching interval, this total charge needs to be a net zero. That is, QA must equal negative QB in order to keep our capacitor voltage at an average DC value. So similarly to the inductor, where in the inductor, if the volt seconds applied over an interval is not equal to 0, our inductor current will walk off. In the capacitor, if the net charge into the capacitor is not 0, our capacitor voltage will walk off. And we can use these ripple current and ripple voltage expressions to calculate the required inductance and capacitance. And what you'll notice from each of these expressions is that the required inductance and capacitance is actually proportional to the inverse of the switching frequency. So as our switching frequency increases, the required inductors and capacitors will decrease. The final thing to point out is the waveform for our input current, IN. So going back up to the top, that is the current entering from the source supply. And the input current is equal to our throw 1 current, which is simply going to be equal to IL during interval 1 and 0 during stage 2, during the interval of stage 2. And most of the time, our source supply will not like an intermittent waveform like this. Our primary power source would prefer us to draw an average or DC current in most situations, which can mean that we may require a filter on our input. So in the diagram above, we've shown just a voltage source, but if we need to filter it, we might have a circuit that looks like this. So here's our source. We might place an LC filter connected on the input, which is composed of an inductor as well as our input capacitance. So you can see that while this current right here, if we call this IN, can fluctuate according to the blue waveform, the source current, IS, can be designed to be very stiff. It can be a DC value. This completes our analysis of the buck converter. In the next series of videos, we will be doing a similar analysis for the boost and buck boost converter.